back, everyone. I hope everyone's trip or staying in was relaxing. I was at a conference on small angle scattering all week, so I am still very tired, and that is the reason why we don't have a homework 4 posted yet. So I promise today or tomorrow, homework 4 will be posted, but again, it'll be usual. We'll have about 10 days or so to work on it. So we have a couple office hours to cycle through, so hopefully it won't be too imposing. So we're going to get back into it then. Now, as a refresher, we were talking about multi-component equilibrium. So from single component equilibrium, what we learned was that the Gibbs free energies were constant across phases. Then we calculated the fugacity of each component across these phases. Now for multi-component, it's a little bit different. It's the partial Gibbs free energy being equal across all phases for every species. So if you have a 6-component system with 3 phases, that means you need to have, well, I guess 3 times 6 is 18 different equations that all have to be solved simultaneously. Well, that's not quite true. There's probably some dependencies there. Probably 12, I would think. Right? So if you had a gas, solid, liquid phase, right, which is not out of the ordinary, or actually rather a liquid gas phase for something like a crude oil pipeline would be something that's very characteristic. Right? So you could have material vaporizing into the vapor phase, you could have material dissolving into the aqueous phase, you could have aqueous stuff dissolving into both of the other ones. So when it gets to be large number of components and large number of phases, things can get very complicated very quickly. Now, the partial Gibbs free energy is defined as how the total system Gibbs free energy changes when you add a little bit of component I, holding temperature, pressure, and all of the other species constant. So temperature, pressure, and then Nj component not equal to I component. Now the problem with this approach is that if we take a look at the Gibbs free energy of a mixture as a function of the mole fraction, it looks something like this for an ideal system. So even in the simplest of cases, it looks complicated like this. Now the difficulty here then is that the partial Gibbs, which is related to the slope of this curve, goes to either, negative infinity as x of 1 goes to 0, or it goes to positive infinity as x of 1 goes to 1. This is even in the simplest ideal scenario, so even for an ideal gas. So to overcome this mathematical complication, which is primarily kind of a nuance, or a hassle, for systems that you might only have weak solubility, like an oil and a water phase, this becomes really difficult and it's a numerically unstable system. And when we get to real system thermodynamics, a lot of the complexity is going to be coming into the numerical methods. And one example that I talked about previously is in reservoir modeling. So if you're trying to do a flow model of oil and water flowing through porous media in a reservoir, you might have a couple of square kilometers or cubic kilometers of area or volume that you're trying to model. And you're going to be breaking those down into centimeter-sized voxel volumes. So you might have billions of different little elements that you're trying to compute the phase behavior in. So just trying to numerically get to a stable solution or a stable procedure that lets you know what's the composition of each of those boxes, whether it's liquid and liquid or vapor-liquid equilibrium, because those are going to have different flow characteristics. And so there is a lot of numerical complexity that's associated with this. So to overcome that, what we did is we defined the partial fugacity. And then the partial fugacities are constant across all phases. So let's say we have a 3-component vapor-liquid system. That means we're going to have to solve simultaneously that the fugacity of species 1 in the liquid is equal to the partial fugacity of species 2 in the liquid. We're going to have to make sure that the partial fugacity of species 2 is the same as the partial fugacity of species 2 in the vapor. The partial fugacity of species 3 in the liquid is equal to the partial fugacity of species 3 in the vapor. We're going to have to ensure that the temperature of the liquid is equal to the temperature of the vapor. The pressure of the liquid is equal to the pressure of the vapor. We're also going to have to ensure that the composition of the liquid phase is consistent. And the notation that we're going to use for liquids is X, denoting the mole fraction. So all of the mole fractions have to equal to 1 in the liquid. All of the mole fractions in the vapor have to be equal to 1 as well. So for a three-component multi-phase system, we have 1, 2, 3, 4, 5, 6, 7 conditions that have to be satisfied simultaneously. Now here's the complexity of this process. If I change the composition of the vapor phase by, let's say, removing a little bit of component 3 and moving into the liquid phase, that affects every single one of these terms. They are all related, right? So if I change the composition of the liquid, that changes how all the other liquid molecules interact. That changes how they want to go into the vapor phase. So every single one of these is a function of every single other one. So it begins to be a numerical complication and challenge, and that's why we want to try and simplify it down as much as possible using sort of theoretical approaches in thermodynamics. Where we run out of steam, then we'll go to empirical approaches. But since the numerical methods can be very complicated in a real system, right? In an oil and gas system, you might have 100 or thousands of different pseudocomponents. For light hydrocarbons, ones that you can accurately measure with a gas chromatograph, right? Your simple alkanes, your branched alkanes, those will all show up as very distinct peaks in a GC curve. When it starts to get to heavier components, then you'll have to lump them into pseudocomponents. But you might be modeling hundreds of different pseudocomponents all simultaneously in a petroleum or a real complicated reactor system. Same thing with like a biofuel or anything like that we're upgrading it. Okay. So what we need now, we need a method to calculate the partial fugacity in the liquid phase and the partial fugacity in the vapor phase, and then by extension, partial fugacity of something in the solid phase. Then that basically covers all three phases. I'm not going to deal anything with anything as complicated as plasmas. So we'll have to leave that to another class or something that I am not familiar with. So what we're going to start off with is vapors. It's a bit easier and more theoretically rigorous. When it gets to liquids, things kind of fall apart a little bit. So to start off, so for the partial fugacity of vapors, now I use the term vapor here because specifically if it's a gas, it's a little bit different of an approach because a gas cannot be a liquid. We can model gases dissolving into liquids, but again, this is something we call a non-simple fluid. By its nature of being a gas means it's supercritical, means it cannot have a phase transition very trivially. But there's a way we can approximate these things. So the starting point if we take Amagat's law, and we say that the volume of the mixture, which is a function of temperature, pressure, and the composition, actually I'll just write N under bar, like I've used in the past. If we say that this is just equal to adding up all of the individual volumes of each of the individual unique species, so we've already introduced one approximation in this procedure right now. We're saying that the volume of the gases are additive. Now for most low pressure environments, this is relatively going to be a good assumption. From the definition of the partial fugacity, Now, I handed out a sheet with a ton of different ways that we can write these expressions out. This happens to be one of them that's the easiest for us to understand. Oops, I've got to close the brackets here. So if we're saying that the volume of the mixture is just adding up in the individual components, that's effectively an ideal mixture. That means that this term here goes to 0. The behavior of the fluid in the mixture is exactly the same as the behavior of the fluid by itself. If you recall from the ideal mixture properties. So from here, we can write down the Lewis-Randall rule, which is usually going to be the main starting point. So, one note, from now on, x of I is going to be equal to liquid mole fractions, and y of I is vapor mole fractions, just to make things a little bit easier. Liquid-vapor equilibrium is going to be the dominant thing we're going to be talking about, because it's the biggest focus for chemical engineers. That and liquid-liquid separations. Those are the two main types of ways that chemical engineers will face separate. There's crystallization that's oftentimes used in pharmaceutical fields, but it's a much more difficult process to define and create. So by assuming volume additivity and the definition of fugacity, we can come up with this simple relationship here. Now we are just one step away from deriving half of Raoult's law. So how do I get this to Raoult's law? So let's remember Raoult's law. So if we kind of connect the dots a little bit, this left-hand side, that's the partial fugacity of the vapor phase. The right-hand side, this is the partial fugacity of the liquid phase. So we'll talk about this one in just a moment. What is the assumption that I need to go from the Lewis-Randall rule, which is the mole fraction times by the pure species fugacity, to be equal to the mole fraction times by the system pressure? What assumption do I need to make?
Ideal gas.
Exactly, if it's an ideal gas. So if it's an ideal gas, that means the fugacity of a pure species is just equal to the system pressure. That's it. So to take us from any completely assumption-free framework, we have assumed volume additivity for the mixing properties and ideal gas behavior to get us to the, I guess, left-hand side of Raoult's law, or I guess it could be right-hand side, depending how you write it, the vapor side of Raoult's law. And that's the approach we're going to most frequently take. Now, we could be more rigorous and have an entirely assumption-free framework. So first of all, any questions on this approach here? So the vapor side on Raoult's law, volume additivity for the mixing properties and characteristics. So effectively, it's an ideal mixture, and then you have to assume an ideal pure component. So there's two assumptions baked into there. If you just say it's an ideal gas, then of course ideal gases always have ideal mixture characteristics. So that one catches all of them. So instead, we can take an assumption-free framework, and we'll see we'll have to introduce some assumptions in a moment. Okay, so now we're going to take an equation of state approach to get the partial fugacity of the vapor phase. But just to rehash, this is something that we've all calculated already with the van der Waals equation of state when we did the phase equilibrium. That's just the pure species fugacity. So in the equation of state method, we can more or less manipulate this expression here to get it into something that's a bit more convenient for us to integrate. We did not go over this derivation. But I trust it. I chewed up all my chalkboard space. Conceptually, all the information about fugacity is contained within it. So we can kind of decode this equation a little bit. Over here, these are just strictly definitions, right? We're defining effectively this term. We're defining the partial fugacity coefficient, just because it's a nice compact, it's right around 1, whereas this, the pressure can vary as whatever. So the fugacity coefficient is a convenient way to collapse it so that the numbers are somewhere between 0 and 1, 2, 3, something simple numbers. If we look at this part of the equation, this is very clearly the ideal gas contribution to the fluid characteristics. This complicated term here corresponds to effectively how does the partial molar volume change of a fluid when you mix it with real characteristics in a real system. So this is where all of the fun arithmetic lies. And then this Z term always seems to pop up, right, when we change from volume to pressure. Sort of makes sense, right? It's complicated, but if we break it down, really this is the complex thermodynamics. So we've condensed the entire complexity of the system down to effectively one, albeit tricky term. So the key thing is we need to evaluate this expression here, the change of system pressure when I add a little bit of species 1 into the system, but in this case mixing it at constant temperature, volume, and holding everything else constant. So effectively, if I have a system, it doesn't matter how complex it is, and I add a little bit of species 1 or species I into the system, and I measure how the pressure responds, that actually tells me basically everything I need to know in order to understand the complex fluid interactions and the phase behavior of the system. Okay, let me move back over here so I can start the discussion. Well, we'll see how much we lost on that one. All right. So from statistical mechanics, if we assume that atoms are particles, fluids are made up of particles which are atoms, and if we also assume that the total energy of the system is simply the summation of the interaction energy between every single pair of particles. So if I call this 1, 2, 3, 4, this one here is U12, U13, U23, U34, and so on and so forth, where we connect all of these and all the possible combinations. So if we make that assumption that the total energy adds up nicely like that, we can show that the virial coefficient, in this case the second virial coefficient, Bij is an interaction parameter. And if you have zero interactions between particles, all this complexity goes away, all of this goes away, and you just simply reestablish ideal gas law behavior. So if we go through the tedious rigor of calculating this, and note, this is as a function of n, not as a function of x. So to clarify, these are not the same, right? Mole fractions and the number of moles in the system are not the same. So what that means is that every time we see a mole fraction, we have to then replace that as makes it a bit more complicated, a bit more tedious, right? Because mole fractions are all dependent on one another. So you cannot hold one mole fraction constant. You have to vary all of them. They're all dependent. So we're going to skip over the mathematics and go straight to the result to get the partial fugacity of a virial fluid. And we have a big, long equation. The good thing with the approach that we've taken in thermodynamics, though, is that this applies for any fluid mixture. This is effectively 100% generalizable, and the number of assumptions that have gone into this are relatively limited. For this particular equation, we have made one assumption, that the virial equation of state describes fluid properties, and two, that we have binary pairwise additivity. And from that, we have an equation now. The only thing missing is how do we get the Bij terms? So there's a couple of approaches. One, we could try and derive some very fundamental properties from quantum mechanics or molecular simulations, or more generally, it's a tunable parameter from a classical perspective. The idea behind this is that if I have a multi-component system, I may not necessarily know all of the different conditions that the fluid is going to be behaving at. But if I have confidence that the equation of state is valid, then I can make a very few number of individual measurements, tune the model to those small specific sets of measurements, and then extrapolate the characteristics to all the other conditions that we will potentially see in the system. So that's the goal of using this system here. And so then these tunable parameters that we introduce allow us to smooth out any errors and gaps. Okay. Now, moving on to the next one. Now, what is the next equation of state we're going to discuss?
Van der Waals.
There we go. The Van der Waals equation of state. Again, we're going to take a one fluid approach. That's the volume. Actually, yeah, we didn't. B, excluded volume. A corresponds to the either attraction or repulsion between individual particles. So conceptually, which of these two terms do we anticipate is going to be the easiest to accurately model the properties of? The excluded volume or the interactions?
The volume.
Yeah, the excluded volume is much easier. So for this we have mixing rules. Some of these are founded in theory, some of them are just convenience. So for the excluded volume of a mixture, we just basically take an average of the individual component excluded volumes to make it on a per molar basis, which seems pretty reasonable. Now for the interactions, we're going to adopt a very similar approach to the virial equation of state, and indeed that is typically the starting point for all of these interactions. Now strictly speaking, for some equations of state, this concept of pairwise additivity doesn't one-to-one translate, but for the most part, this is the mixing rules that almost every thermodynamic model will end up using. For the most part, that's because the models aren't quite good enough to argue over the details of. And that it's easier just to add in additional kind of tunable parameters from a practical purpose. So in this case here, oops, Aij. So, the next step for a cubic equation of state, in order to use it to solve for phase equilibrium, would be to effectively evaluate this integral. So we would substitute in the mole fraction, summation of the mole fractions here, summation of the mole fractions doubly up here, substitute the mole fractions for the number of moles, and then evaluate a big long integral. So to do this from a generalized perspective involves taking a derivative of an infinite double integral. So it's not particularly pleasant, but it has been done. So I won't write out the equation for the van der Waals equation of state, but I believe the textbook has it listed out and also has it listed out for the Peng-Robinson equation of state. So those may come into play in the homework at some point. But effectively, the procedure itself is tedious. Now, thankfully, for the most part, there are plenty of examples for us to work through dealing with low-pressure vapor-liquid equilibrium. In low-pressure vapor-liquid equilibrium, most things behave relatively ideally. And so I guess I have it all erased, but Raoult's law for the vapor phase is not catastrophically bad. It's really the liquid phase where things go very awry very quickly. Or for the most part, if we do want to use non-ideal characteristics for the vapor phase, we have the mathematics basically already worked out for us. And we have tunable parameters for any particular system. So unfortunately, thermodynamics doesn't have the answer for everything. We have to rely on getting some experimental data and tuning our models to fit the data. And that really is, quite frankly, where we're at in terms of a practical application of thermodynamics. So all the beautiful elegance that we had worked on so far kind of falls apart a little bit. But as a refresher, we never could calculate anything with thermo, right? We always had to rely on experimental data measurements. So the heat capacity, right, was the number one property that we relied on. So with multi-phase equilibrium, it gets a bit more complicated because we have to assume that a particular model is an accurate representation of the fluid properties and then tune that model to fit. It's not quite as nice as just going into a calorimeter and measuring the ideal gas heat capacity. So this is where things get a little bit less pleasant. Now, if we talk about liquids, now this one here obviously won't work because the virial equation of state does not predict the existence of liquids, but we could still use an equation of state approach. So if we have an equation of state that's valid, we can apply these mixing rules to whatever arbitrary equation of state we'd like to, and then just measure the fugacities and the partial fugacities. But these equations are not pleasant. They get longer and more complicated than even the ones that we've dealt with for the pure fluid situations. So if we talk about a liquid, and we look at the forces at play, what is the weakest interaction between two molecules that we know of all the different types of forces that we have going on? What is the weakest type of interaction between two molecules?
Van der Waals?
Van der Waals or dispersion forces. So our weakest, Van der Waals or London dispersion. Right, so this is going to start off on our easy side, right, where it's relatively easy to model. But this is where we're starting at. This is our, what I say, quote unquote, easy to model scenario. Okay, what is the next strongest type of interaction that we talked about in chemistry or whatever physical chemistry course you had previously? A little bit stronger than London dispersion.
Hydrogen bonding?
One step before hydrogen bonding.
Induced dipole.
So London dispersion is effectively kind of an induced dipole. Right? So where one fluid sloshes around a little bit and the electrons move around, and then the electrons in the other molecule nearby move around, and they kind of just sync up and dance nicely, and that's why they're attracted to one another.
Dipole.
Dipole, or permanent dipole, I'll call it. Okay, let's think of an example. What is a fluid where you would expect the interactions to be strictly London dispersion? Give me a compound, a chemical compound.
Hexane.
Bingo, hexane's a great one. Permanent dipole. What's an example like this?
Water.
Not quite.
Maybe an alcohol or something?
Yeah, something like ethanol, methanol, acetone. These are all going to be permanent dipoles. You're going to have electrostatic positive and electrostatic negative regimes. So acetone, if I don't screw this one up. Right, this is going to be slightly negative, and I guess in chemistry, right, you write it as delta negative, and over here you write it as delta positive. Not a full charge, but a little charge. Okay, next one we've already covered. Hydrogen bonding. And the last one, what would be a really, really, really strong interaction between particles?
Bonding.
I think you guys said it. Everyone said it at the same time. Charged and coulombic. Those are very strong interactions. Right? They basically form crystals. So with fluids, we have a lot of possible things going on. And how we talked about that example at the end of last week, where we said if we were all ideal gas molecules, how many would fit in here? And it was like 2 or 3. and if for a fluid it was 3,000. So if you're a little bit off on the interactions between the molecules, the inaccuracy on liquids just really drives your approach into the ground and really kills any approach you have. So instead, how we get around that for liquids is we just basically forget about the whole thing. We just say, you know what? We don't have models that are good enough to fully describe every characteristic of the system. So what we're going to do is we're going to come up with a model of how we think the fluids behave, and then we're just going to directly calculate this partial fugacity coefficient. So in liquids, the strategy is that our goal is we want to get to the partial liquid fugacity, and this is going to be a function of temperature, pressure, and now we'll write everything with x just as a convention, right? But, just the mole fractions, whatever you want to use. What we're going to say is we're just going to say, you know what, let's just directly calculate something called the activity coefficient. So here we have the mole fraction, we have the activity coefficient, and pure species fugacity, pure I fugacity. So now the key question is, we're going to spend a lot of time talking about activity coefficient models. And that is going to be the approach. So, looking at activity coefficients. If I have a plot here of the excess Gibbs. Now recall, this matters. Give myself a little more space here. The activity coefficient is defined effectively in this form. As the partial molar excess Gibbs, which is defined as, I'm leaving out the little subscripts. So the activity coefficient is effectively related to the partial molar excess Gibbs. That's a lot of conditionals. Right, so let's go through this a little bit. So if I look at a plot of the excess Gibbs free energy, and let's say it looks something like that. One of the complications is we can't actually really measure directly the partial excess Gibbs. We have to sort of use an ideal gas mixture type model, and then we can basically calculate it from volume expansion and calorimetry type experiments. Or more directly, we actually measure the vapor-liquid phase equilibrium between two phases, and everything that doesn't add up as a result of Raoult's law, then basically we have to say that's coming from the excess Gibbs. So we more or less have to get here from somewhat of an indirect way measuring experiments. But let's say we do have a plot of the excess Gibbs, and we made a few experimental measurements here. The only reason why we care about plots that kind of look like this to some extent, well, that's not entirely true. For liquid-liquid equilibrium, we really only care about this because this means that the fluids don't like each other. That means when you mix, they deviate positively from Gibbs. If you had negative excess Gibbs, then you really would never have to worry about a liquid-liquid phase separation type problem. So the first and most simplest approach is, okay, I've measured the excess Gibbs free energy of my system based on actual measurements of, let's say, vapor-liquid fluid equilibrium, or maybe liquid-liquid fluid equilibrium. There's a number of different ways to get at it. The simplest activity coefficient model is just say, let's just fit it with a polynomial. So what I'll do is I will just model the excess Gibbs of the total fluid mixture with a polynomial. Now the simplest polynomial is I'm just going to fit it with a quadratic function. So if we rewrite this, it does end up being a quadratic function. And then we could kind of distribute this, right? A x1 minus a x1 squared. Now this is a Redlich-Kister polynomial. I don't expect you to memorize that name, but we talked about this type of a polynomial. And it's good because at either x1 or x2 equals 0, and x1, x2 equals 0, it gives you cross the axes, which is good. Questions? This is ringing a bell a little bit. So, in order for us to get an activity coefficient model that we can then plug into and find our phase equilibrium, we need to evaluate the expression that the partial excess Gibbs is what we're trying to calculate, which is then related to our activity coefficient, right, is equal to, in this case, let's do it for species 1, plugging in our activity coefficient model. Partial excess is the number of moles times this, all this fancy mathematics. So effectively what we're looking at here is n a x1 x2. All we did was substitute the different terms. Partial excess Gibbs is the partial derivative of the system excess Gibbs free energy. We're modeling the excess Gibbs as a polynomial, timesing it by the number of moles. So we see here that x1 and x2 are actually functions of the number of moles of species 1. So we could either do a lot of chain rule type stuff, or we could rewrite our expression. A is a constant in this case. Okay, so in this case it's going to be I'm going to write this out so I can show you all the full steps. So this is going to be n1 plus n2. This is just our n. n1 over n2. That's our x1. n2 over n1 plus n2. That's our x2. Then we have to take the partial derivative of this. So I'll skip over the mathematics in the interest of time, and we'll get to our conclusion that the partial excess Gibbs for component 1, if we model the excess Gibbs as a parabolic parabola, basically, we get, it simplifies down to a nice convenient. And likewise, if we repeat this for the other side, or we just apply the Gibbs-Duhem equation, and this is called the one constant Margulis. So if we want to look at a plot of what we get out of this expression, the one constant Margulis equation is symmetric. Let me just write this out actually one more way here. So RT that actually gets us to our activity coefficient. So the tricky thing about activity coefficients is they're exponential. They're exponentially dependent on the concentration, which means a very small change in concentration can really wreak havoc on things. So the one constant Margulis ends up looking like this. It is symmetric. The fluid, so in this case I'm trying to walk it through which one is which. So as the activity coefficient drops off effectively towards 1, that means that the fluid is almost 100% pure. It's going to have very little influence from the multi-component mixture. So in this case here, this is going to be activity coefficient of species 1, and this is going to be activity coefficient of species 2. So if I'm component 1 and I'm at a very low concentration, I'm going to be surrounded by molecules of component 2, and I'm going to be extremely unhappy with my surroundings. Likewise, if I'm component 2, right, and a little bit of 1 gets added, I don't really care. As more 1 gets added, eventually component 2 is going to have to be around molecules of component 1. So this is going to impact multi-component, multi-phase equilibrium. So if I have a liquid mixture that's, let's say, x1 is equal to 10%, x2 is 90%. If I have a non-ideal mixture that looks like this for the activity coefficients, that means component 1 is going to probably try and go to the vapor phase more readily than you would expect just based on its vapor pressure alone, because there's an additional penalty of it being surrounded by component 2 molecules. That conceptually makes sense. Now this approach can be expanded effectively just using different polynomial fits. So if we take this Redlich-Kister polynomial expression, and instead of just modeling it as one parabola, we add a few more terms. Right? And then we can just keep on writing this actually. Plus C. This polynomial expression form, it just gives us more and more refinement, more coefficients that we can tinker with. If we just take the first 2 expressions in the Redlich-Kister polynomial, we work out the same exact math, we'll come up with a 2-constant Margulis expression. Let's see, I might have it, I think this is cubed. I have inconsistencies. I have one expression has cubed, one has squared. So I'll have to double check that. So these coefficients here, power to 3 or power to 2, they might be a little bit off, unfortunately. I'm not sure which of the 2 is right in my notes. All this gives us is more refinement. So instead of 1 tunable parameter, we effectively have 1, 2, 3, 4 tunable parameters. Another common one is the Van Laar activity coefficient model. Again, all this is just a different form of a polynomial fit. Now these are all empirical approaches. There are other analytical approaches. There are correlation approaches. Right? So I don't know if you recall from an undergraduate, for those of you who are chemical engineers, when you're in senior design, you have to really build a chemical plant. A lot of times you're using Aspen or some other process flow simulator. And then you go to the fluid phase modeling for your distillation column. And you say, okay, which model should I use? And there's Wilson, NRTL, Uniquac, Unifac, Van Laar, all these other ones are basically just, to some extent, empirical. These ones here are all empirical models, but they've been tuned and measured to different systems. But there are a lot of other ones that are trickier, more complicated, and a little bit more theoretically rigorous. And we'll be talking about them as we move forward into specifically liquid-liquid and non-ideal vapor-liquid equilibrium. Okay, any questions? All right, I will post the homework very shortly, and so see you guys later.